to numerical ship and offshore hydrodynamics. Today is the lecture 55. Now, today we are going to continue that what we have discussed in the last class. In the last class, we have discussed some part of the structural analysis FEM. So, today we are going to continue the same, and these are the keyword that you have to use to get this lecture. Okay. So, let us start. Now, if you remember in the last class, we stopped at this point where we actually define how to get the shape function. Now, here looking at this expression, you may be confused because it is defined from -1 to +1. So, let us not bother about this. This is actually representation of the local coordinate system. I am just going to show you that how a cubic polynomials look like and how the shape functions is look like, right. Remember that what we have discussed there is in the global reference frame, that is why we use x 1, x bar etcetera. But again when you do the integration or numerical integration, we are going to see today. So, that time while you need to do that, you need to again transform back to this local coordinate system -1 to +1. So, that part let us leave for this moment. So, if you remember in the last class, we have defined the shape function n 1, n 2, n 3 and n 4, and then we write our the global displacement or W x, this equals to in terms of a shape function, right. So, in terms of a W 1 into n 1 x, and then plus of course, for the element E, let us not forget the element E, and then it is del W E into del x into n 2 x, right, plus again now it is for the second element W 2 E into n 3 x, and then plus which is the del W by del x for the 2 into n 4 into x. So, this is how actually we wrote the displacement. The similar way that the test function also we can write that V x, that is the text function that we have used in the last class. So, that also we can write as some V 1 into of course, element T into n x plus del V 1 del x, the slope for the element E, del V 1 for the element E, again it is n 2 x, then it is V 2 into n 3 x, of course, for the element E, plus del V by del x for the element E 2, which is into n 4 x. Now, this is my that how I approximate. Now, if you want, like you can use also the x bar etcetera, because these are the approximate solution. Okay. Here you can use the x bar also. I am leaving all these things, right. Now, the next job is substitute this W and V in the original that weak form solution. Now, what is the weak form solution? If you remember, it is 0 to L into m into which is del W by del square W by del T square, right, and we multiply this with my shape function V x into d x, right, this one, and then plus 0 to L, and this one is E into I, which is del square W by del x square, remember, and also you need to multiply with this V x into d x minus integration 0 to L, which is V 1 x into f equals to 0. Now, this is actually my formulation, and you can just, if you want to mark, you mark equation, let us say 1, something like this. Now, what you need to do is you need to replace here you need to replace all the I mean the W and V. Okay. So, now if you substitute this W x and V x in this equation 1, then what you get? So, you get 0 to L m. Now, I can write instead of del square W by del t square, I can write W double dot. Okay. So, therefore, just substitute over here. So, you have W 1 double dot E into N 1 x plus which is del x of W into double dot into E into N 2 x plus W 2 double dot E into N 3 x and then plus again del W dot by del x 2 for element E into N 4 x. Right. Now, here I am not going to only for mass matrix I am actually splitting. I don't split the other terms. It is not necessary. In a similar way you can break these two. But now let us see that here you need to multiply by the test function V also. So, then it is V 1 E x into N 1 x plus del V del x into 1 into E into N 2 x plus V 2 E into N 3 x plus del V by del x 2 E into N 4 x. So, this is how I write. Now, what I do over here, now I take this common. Okay, of course, I forget this summation E equal to 1 to any, right, because I need to do this integration in for all elements, right, and then plus if you want you can write the other term, then make equal to, then you make this equal to 0. I am not writing the other terms. Okay, I am just writing this the mass term. Similarly, you can substitute here the same thing, this equation you can substitute over here, and also this equation is substitute over here, and then you can do the things, right. Okay. So, having said that, I am having this expression. Okay. Now, I am writing this expression, I am taking that V 1 x common. Okay. So, if I do that, now my next job is basically I am taking this V 1 E x, I am taking this common, and I let me write the other stuff. Okay. So, if I take it common here V 1 x, this multiply with this element, right. So, I just write over here. So, V 1 x equal to m into W 1 double dot, right, and multiply by the N 1 x, and also you can see here this V 1 x is also multiply with N 1 x. So, therefore, I just multiply here also with N 1 x, right. Now, we take the next term, of course, I should not forget that 0 to L into dx, it is always there, right. So, and then again I just write 0 to L. Now, I take the next term which is del W double dot by del x at element E for 1, right, and then you should multiply with N 2 x. Now, since V 1 is always with N 1 x, it is N 1 x, and then it is dx. Now, similarly you can write the other two term also, right. So, here let me write again the third term, which is 0 to L, and remember of course, it has like E equal to 1 to any, of course, it is there, right, and then it is under this bracket. So, now again if I take V 1 x common, next term will be m multiplied by the W 2 double dot into n 3 x and again multiply by n 1 x into dx, and then the fourth term remains, which is nothing but 0 to L. We have m, then it is del W double dot by del x for the second element for E into n 4 x into n 1 x, right. So, then dx. So, I close this and then I mean I should not close this for this, because you have another term, again the similar term can be written for my for this del square W by del x square into those term also I need to do E I into. So, for that also you need to do that, and then also you need to do that for the another term, which is nothing but integration 0 to L here I just. So, another term 0 to L into V 1 x into f, right, this equal to this. So, you have to do all this term also, right. I am focusing on only this and not also the focusing fully. I am writing this for V 1 x. Now, similarly basically I can do the same for del V 1 E by del x also. If I take common, and then again I can have the similar term, right, is it not, and then plus I can have this V 2 E, again I have the similar term, and then I have this del V 2 by del x, right, for the element, or you can say 2 over here E, and again you can have some similar term, right. It is very easy, it just you have to be patient and you have to write the term. So, I just take common for V 1. Similarly, you can take common for this the second term, which is nothing but del V 1 del x, right, and then you try to figure out what other term left, and you can do all these things. Now, idea is after having this all exercise, what you are going to have as follows. Now, after you do all these things, then actually what you are going to have is, now for in case of a mass matrix, you have some term with V 1 x, and if you take a common, you have some terms that is the part of the matrix M, right, and then you have some term which is again coming from the stiffener term, that the second term. So, let us call as a k. I am just writing in this way. Okay. Similarly, if you take common like del V del x and it is 1 E, and you do the same thing, right. As I said, you substitute everything in the second integral, like that integral is nothing but in 0 to L, which is E I del square W by del x square into, here you have the V x into d x. So, in this here, if you split again W and the V, that with the test function, and again you take everything common, then you have some component with, if you take a common V 1 x, you have some component definitely here. Similarly, in case of here also you can have some component this M, right, and then some component again having with the k, and so on. So, again you have take V 2 x common, and then you have like this M. In fact, you have some term from the external matrix F also, right, because here also sorry here in this equation also, if you substitute this V 1 x with this definition, definitely some component you are having with this F matrix also, right. So, frankly speaking, okay, let me refresh it again. So, if you take this common V 1 x, then you can have some component, let me write as m, some component I am writing as k, and minus some component as in having a f, something like this you can have, right. And similarly, if you take del v del x E for element E, again you have similar this 4 component, right. Then plus if you take this V 2 E, again you can have this component, and if you take del V del x to E, again you are having this component that is equal to 0. Now, initially if you remember, I said that orthogonal property, under this orthogonality I called that this error function and this test function V 1 is the norm equal to 0. So, that is the idea. Now, if these are independent to each other, now if this has to be 0, then all this term associated with this should be equal to 0. So, if I do that, then actually you can have 4 equations. You have one equation for this, one equation for this, you have one equation for this, and you have one equation for this, right. So, this is the idea. Now, you see I have 4 unknowns. My 4 unknowns are what? My 4 unknowns are W 1, del W del x for 1 for each element, then I have W 2, and then I have del W del x 2 for each. So, I have these 4 unknown, and now I have individually all these 4 should be equal to 0, right, is it not. So, for each element you are having this one, right, is it not. So, this is the idea. If you do that, then actually finally what you are getting is, finally you are getting a a matrix. You have some 4 matrix, right. I mean, if I write everything in matrix form, then how do I write it? So, if you want to write in a matrix form, then definitely you have a matrix M, and then it should be, it is, now I just write D double dot, because you see it is D double dot means it is a column matrix, it is W 1 double dot del W del x for element E double dot, sorry, then W 2 double dot, and then del W dot by del x to E. So, I have these 4 elements, right. So, therefore, let me rub this thing first. Okay. So, therefore, this is actually your 4 cross 4 matrix, and this becomes 4 cross 1 matrix, and then you have again, as I said, is a K matrix. If you do this other term, it is again it is 4 cross 4 matrix, and it is multiplied by the displacement matrix D, and then minus you have this, or you can take the other side of this, which is the F matrix, and which is again this 4 cross 1. So, this is we can call is a element matrix. So, it is a localized. Now, this is one. Now, here this you can also confirm that this, let me first write it here, this element m I j is nothing but 0 to element L E, this integration m into n I into element E, n j into element E into d x. Now, again this k I j, this term should be 0 to L E into E I, which is del square n I E by del x square into del square n j E by del x square into d x. Okay. And also you can write this f equal to 0 to L E, which is f I or f E element matrix into n I x into d x. Now, you see I can see that this is same. So, you can just verify the first one here. You see I multiply v 1 x, which is now if I multiply this with this, so what you get? Okay, let me write in the right hand side. I just rub it. So, I just write only one you can understand. I just take a common v 1 x and let me write that what term I can have. So, first one is w double dot into 1 into E into n 1 x and you have n 1 x. Now, you see you are having this term. So, this is your m 1 1 term, right, is it not? Now, similarly, the second term would be del w dot by del x 1 into E, and it should be, it is here n 2 x into n 1 x, right, and of course, you have the multiply with m. Now, you see n 1 2. Now, your 1 refers for w 1, your 2 refers for del w del x for 1, your 3 your 3 refers for w 2 and your 4 refers for del w del x 2. Now, you see you can just break it up, you can get this is the composed way, you can get this expression, fine. Now, once you have this local matrix, now you need to convert this local matrix to the global matrix. Okay. So, now how we can do that? Now, here what you need to do is as follows. Suppose I have now this is the beam. Now, what I am going to do is I am break it up with the n number of element, right. Now, I break it up the n way. So, I take any E, take element E, and then I define here it is w 1 del w del x 1, w 2 and 2 del w del x 2. So, here you can see, now let us start with the first element, second element, third element. Now, if I have the any number of sections, so definitely I have any plus 1 number of node, right. So, here now what I need to do is I have n 1, I mean that element 1, here I have w 1 and then del w 1 by del x for the element 1, and here also I have w 2 and del w by del x 2 for the element 1, right. So, here I have the contribution from the element 1. Now, when I write for this second element, so here my w 1 and del w del x for the second element, and then I have this w 2 and del w del x for the first element is the same node, right. So, therefore, I need to have a mechanism to make it globalized, right. So, how do I deal with? What I do is I make each node as w 1, w 2, w 3 and here of course, it is w n plus 1 or n e plus 1 whatever. Okay. Just make it w n e plus 1. Okay. Now, each node I have 2 degrees of freedom. So, therefore, here also I have del w 1 del x and similarly, I have here at the end node I have del w by del x which is n e plus 1. So, therefore, the total number of the nodal element I have or nodes I have, it is 2 into n e plus 2, right, n e plus 1 for this w and again n e plus 1 for the del w del x. Now, I need to write the whole thing in the form of there is no element will be there. So, I need to write a global mass matrix M which is multiply by this element which is w and of course, del w del x. Similarly, I just going to write this Tifton matrix K, again I have this matrix del w and del w del x and then I have a matrix the right hand side which is the force matrix. So, then what is the dimension of this matrix? It should be 2 into n e plus 2 cross 2 into n e plus 2, right, and this one is nothing but 2 into n e plus 2 cross 1 and so on, right. So, now my job is how do I write this element matrix. Now, for that actually we use some kind of a connectivity matrix, right. Now, what is this connectivity matrix? Let me try to explain. Now, thing is that here this you have this w 1 then w 2. Now, these are the global. So, I am not writing E and it is w 2 into n e plus 1 or something like this. Now, I write this matrix connectivity matrix as this is 1, 2, 3, 4. Now, again now you see here this 1 2 corresponding to my element stiffness matrix E 1 and del w del x for element 1, right, and 3 4 corresponding to w 2 and then del w del x for the for that same element 1. So, now I break it up into 4. Now, then effect of this also will be there. So, when I write this second matrix it should be 3 4 5 6. So, this 5 6 again for the third element it will. So, when I write for the second element I am taking the contribution from the first element also. Similarly, when I write for the third element, so I need to take this contribution of the second element. So, I am writing here 5 6 7 8 and so on. So, this is called the connectivity matrix and finally, it should be 2 n minus 1 2 n plus 1 into 2 n plus 2. So, this would be my connectivity matrix. So, I use this connectivity matrix to get this the global transformation of the global matrix to the local matrix to the global matrix. Now, here I am just writing just a pseudo code for you and then it is your job to you substitute this pseudo code in the matrix and you check that whether you are getting this effect or not. Okay. So, now this code goes like this way. Now, just take E equal to 1 to n e. So, this is the total number of element. Now, you have this element wise you have 1, to 4 and then okay, I just take 4, this is a MATLAB code 4 and then you have j also equal to 1 to 4 and then you are writing, I am just writing for the mass matrix and the stiffener matrix and also the force matrix also is the same. Now, I can write here m of C of E comma I. So, it is a 2-dimensional matrix, right? The m is a 2-dimensional matrix. Then C of E comma j should be equal to this mass matrix C of E comma I comma C of E comma j plus, now I am writing this m dash is the local element which is E comma I comma j. Okay. So, then you can simply your end the j and then actually you can here similarly you can write k also the similar the same thing. So, I am not repeating for the k also you can write the same thing and again now your global force matrix F, okay, just F and this is again C E comma I and now it is a 1, it should be the n plus 1 plus 1 matrix, this equals to F of C of E comma I plus F of E comma I, okay, and this is end of I and then this is end of E. Now, it is your job. Okay, so, this force matrix it is not okay, visible. I just write it in just top so that you can see that F of E comma I. Okay, now you can see it, right. Okay. So, now so if you use this pseudocode and once you use this pseudocode actually you can get this this local matrix into the global matrix. Okay. So, it is your job to put these values. I do not have much time to show you that, but you can take this as a homework and you can check that actually it is happening. Okay. So, once you have this, then actually you can get this global matrix over here. Now, once you have this global matrix, now it is a differential ordinary differential equation, right. Now, once you have this ordinary differential equation, I already take lot of classes how to get the velocity and displacement from this ordinary differential equation. We are using Euler scheme. You know, apart from that actually you can use Newmark beta method, you can use the Runge-Kutta method, you know how to solve this equation, right. It is very simple, as you know that I am just showing you that if you remember we are having this m x double dot is equal to f, we solved it quite often, like then you take it is 2 degree, I mean equation of degree 2 you have to convert for degree 1. So, we take x dot equal to v. So, then we can convert into v dot is equal to f and then we are using the Euler scheme, right. We are using Euler scheme, we are getting v t plus delta t equal to v t plus m sorry f by m into delta t and so on. Similarly, here also you can have m into x double dot in this form. So, k into x dot plus c or sorry c into x dot and then plus k into x equal to f. Now, here you can see that where this c term is coming. Now, this damping term actually externally you need to add and then lot of literature are available for this. You can use anything any damping scheme. Okay. So, normally we are taking this damping matrix is the ratio between the mass matrix and the stiffness matrix. So, you can take this C matrix it is something of alpha into m and then some beta into k. So, in this form actually also you can take a damping. So, you can check it out like that how to add the external damping. Okay. Anyways, in fact this you just check the Rayleigh damping is the most popular one actually, that is what I explained little bit. So, you can check it out. So, similarly here also instead of that we can write as, now here we have m into u double dot plus c into u dot plus k into u equal to your external matrix F. Similarly, also here you can same way you can write this equal to F minus C u dot minus k into u, and then you can find out the solution for I mean you can get this displacement u as well as the velocity u dot, right. So, this is all about the structural solution of this hydroelasticity problem. Okay. So, today we are going to stop, and maybe from the next class we are going to discuss some other way of solving the same problem. Now, here we are using the finite element, and then in next class maybe we can see the same problem, but the solution technique not finite element, it may be the modal superposition technique. Okay. So, with this we stop over here. Thank you.